Hey guys, we're going to move right into membrane transport here in a second, but before we do, I wanted to add a little medical relevance, like real world, who cares kind of relevance to the cell-to-cell adhesion molecules we talked about last time, the tight junctions, desmosomes, those kinds of things. A buddy of mine that I went to grad school with ended up going and doing a postdoc at Syracuse University at Upstate Medical. And his whole area of research was on breast cancer. And he looked at specifically how it was that breast cancer cells would detach from their neighbors to metastasize, which means it would go into the bloodstream or into some other vessels, the lymph system they call it, and how was that the tumor would break off and form another tumor in another place. And so, these things that we're learning, they seem a little bit detail oriented and something that really don't matter, but they really do. His research was all about that and how it is that we could lessen the chances that a cancer is going to spread. So I just wanted to mention that as kind of an interesting fact about some of these cell adhesions. All right, so today, this particular clip is all about membrane transport. Remember, the plasma membrane is a boundary. It's very important for controlling selectively what it wants to allow through into the cell or out of the cell, what it wants to keep inside and what it wants to keep outside, okay? So, key terms here, this phrase, selective permeability. You want to have a good definition. It's the selective property of the plasma membrane to maintain its integrity so that various items can be limited as to their moving across that boundary, right? So selective permeability is about nutrients that the cell wants to keep inside, valuable proteins that it wants to keep inside, and nutrients that it wants to move inside. So it wants the good things in. It wants to bring them in and keep them in, right? It also is going to be involved with getting the undesirable wastes to pass out of the cell while keeping out the undesirables that are out there, right? So you want to bring the good things in, keep them in, and you want to push the bad things out and keep them out, right? Kind of makes sense, right? That's what we want to do with each cell to keep them alive and healthy. Now, there are lots of ways that items can pass through the cell membrane, right? And understanding how these all work will depend on our knowledge of what makes up that membrane. We have phospholipids, remember, right? Certain properties about the phospholipids. They're like an oil boundary. And then we have these proteins, some of which are transmembrane and go clear through the plasma membrane, some of which have holes in them, right, that allow certain things to pass. Some of these processes by which things will move across that membrane, either in or out, can be passive. So if you're passive about something, you just kind of hang back and you don't care, right? You don't care one way or the other. Okay, so with a passive process, there's not a lot of energy put out, right? And there's not a lot of energy input into a passive process. But if you're actively trying to do something, active processes, this would require some energy, right? It's an active process to move something from one place to another, whereas passive processes don't require a lot of energy. So this would be one way to keep the two things apart. If you hear about something that is moving across the membrane with no energy input, you got to think passive. Even if I give you a specific example, I'll give you one right now. Water moves easily across the plasma membrane with no help at all. No energy expenditure. You know then that water moving across the membrane is a passive process. okay? So we're going to have a good handle on what kind of processes are passive and what kind of processes are active when it comes to this movement, all right? Now, this is just a breakdown. This is going to help you to keep them apart, keep them in their categories. I'll give you major hints as we go through lectures about what questions I'm going to ask you, and you'll want to pay attention, right, so that you are kind of ready for those kinds of questions. So here we have, listed under passive, a whole bunch of subcategories of types of passive processes. Here we have some types of processes that are active. Now I'm going to go over each of these with you, but in a multiple choice question, if I were to say which of the following processes is a passive process, and I list exocytosis, endocytosis, active transport, and facilitated diffusion, you want to pick facilitated diffusion because it's a passive process. If I say which of the following is an active process, I put 3 of these guys up here, and exocytosis. You know exocytosis is the choice. If it's a true-false question, right? In the process of moving water across the membrane, there is no energy input, and this occurs by the process of exocytosis. Well, there's a problem with that statement, right? Water may be moving by osmosis across the membrane, but that is not exocytosis. If osmosis, you know, is a passive process, right? So I'm going to throw these kinds of questions at you. You want to know your categories. You want to know how these are arranged when it comes to this, okay? So first thing we're going to do is we're going to hit passive processes. We're going to go over a lot of these passive processes in this particular clip, okay? So first, let's tackle it by considering and remembering what a plasma membrane is made out of. Here we have our negatively charged phosphate groups, and we have our, which are hydrophilic, right? They like the water that they're next to. And then we have these long chains of carbon, which have nonpolar covalent bonds, so they're going to be hydrophobic, right? And they're pointing towards one another, and for good reason, right? These fatty acids don't want to be pointing out towards the water, extracellular water or intracellular water, okay? Now, in the process of diffusion, we would say that molecules that move from the water on one side to the water solutions on the inside, right? These are just fluids. That these molecules would naturally move down their concentration gradient. This is a natural tendency, and it's a passive process. So let's think about this. If I go into a room and if you go in and you spray perfume, right? Or like some people in my lecture halls, they're like, it's like they drown themselves in perfume, or these guys that walk in with just so much cologne on, will kill you, you know? And they might be in the corner of the room, and I wouldn't smell it from way down in the front of the lecture hall. But people closer to them would smell it, right? It's going to permeate. It's going to go from high concentration to low concentration. Eventually, maybe I'll smell that, right? Because it's going to move high to low. This is a gradient, concentration gradient, that perfume or cologne molecule is moving through the air. Well, molecules like that move in a water environment as well, from high to low. And if it doesn't require energy, you don't have to put in energy for that perfume molecule to move, then we say it's a passive process. Now, in order for something to move across this bilipid layer, right? It's got phospholipids pointing both directions, and this is like an oil boundary. Remember this, right? Because of those fatty acids. What this means is that anything that is hydrophilic, let's take this water, and we consider a charged item that's dissolved in that water, like sodium, right? It's a salt, it's a cation. Well, sodium is not going to easily pass through this hydrophobic regions. Sodium is hydrophilic. It's got charge. It likes hanging with water, right? It's not going to move easily through our phospholipid bilayer. It's going to be rejected. So this diffusion will not happen easily, high to low. Let's say there are more sodium ions outside here and less inside here. Well, sodium will want to move from high to low, but it's not going to go through here because of this oil boundary. It can't get through there. Okay? What, however, will make it through our phospholipid bilayer would be something that does not have charge. So let me give you an example. We have two oxygen atoms bound together, sharing electrons. You might also refer to it as oxygen, O2, right? This is dissolved in the water, let's say outside of this cell. And let's just say there's more of it on this side, okay? Oxygen will naturally want to move from high, I'll put H for high concentrations here, to low on the other side. Guess what? Oxygen and oxygen, warring for electrons, are going to have non-polar covalent bonds holding them together. They are not going to have more charge for those electrons on one side than the other. They're going to be making a fairly uncharged situation, right? This oxygen molecule would wiggle right through this boundary with no problem. So it would move in a very simple way without any help across this phospholipid bilayer. It would have to be an uncharged or lipid soluble item, right? Because it's gonna be going through this oil boundary. And it would have to be a small molecule to do this. Okay? So it has to be small and uncharged. Okay? Another example of something that does this would be a steroid hormone. Like testosterone is made out of fatty acids, basically, and it would move easily through the boundary. Okay? So diffusion is just a basic movement of a chemical from high to low, which is pretty much what a passive process is going to be. And to move across the simple phospholipid bilayer, this would have to be a lipid-soluble item. Examples would include the one I just went over, oxygen, because two oxygen atoms aren't going to pull the electrons, those negative electrons, one way or the other, and it's going to be uncharged. Carbon dioxide is another small, uncharged molecule. Fat-soluble vitamins, like vitamin E, for example, these are uncharged. They're small and they go right through. Alcohol. It has kind of a non-polar quality to it, lipid-soluble quality. It goes right through. And alcohols has potent effects on cells as a result. And the one I didn't mention here would be those, but I mentioned it earlier, would be one of those testosterone or estrogen or one of those kinds of steroid hormones that are natural in our body. They would move through simple diffusion. What makes it simple? There's nothing to it. It goes right through here without any help. No proteins involved here, right? It just goes skipping on right through. All right. So we have a passive process of diffusion, and when it goes through without any help, we call it simple diffusion. Let's change this a little bit, okay? What if we consider now, here we have our extracellular fluid, here we have an intracellular fluid. So it's telling us what's the inside of the cell and what's the outside of the cell. And here they have these little red dots. So let's say these little red dots are, in fact, sodium, like we were mentioning earlier, okay? So sodium, and sodium has a charge. And I just described to you why it is sodium would not be able to go through this boundary. Not easily, right? Because this is a This is a lipid oily barrier where charged things do not move. Okay? Something that's charged or larger like that, a larger molecule might be maybe even a whole protein or a sugar molecule, which is a little bigger than an ion, right? A glucose, for example, would be a sugar, and it's got several atoms in it. 24 atoms, actually, versus an ion like this, which is basically one atom with or without an electron, right? So if it is large or charged, right? I'm thinking large and in charge, right? But if it's a large molecule or a charged molecule, it doesn't have to be big, it could be just charged, then it is not going to skip right on through here easily, right? Oily boundary. What we're going to need here would be a carrier molecule or a protein carrier that goes clear through. So here we have our transmembrane carrier molecule. It's made out of a protein, and it's going to be just the right size. It's going to be just the right size to allow one particular type of thing to move, and in this case, let's just say it's a sodium carrier. Sometimes they'll say it's a channel, okay? It's a channel that's always open, and only sodium might be able to fit through there, right? So think of it like a door that's always open for one size item with that particular charge, like we see on sodium. All right. Now, it's still diffusion, isn't it? Lots of dots on this side, only 2 dots on this side. To get this item to move from extracellular to intracellular is not going to require energy. So it still follows the rules for a passive process. However, it's not simple like before. It's not just skipping on through the phospholipid bilayer. It needs help. Facilitation, right? Facilitation is help. If you facilitate the movement, help the movement, we call it facilitated diffusion for these types of items. Doesn't mean it needed energy, it just needs a little help by giving it a channel to move through. All right. Now, there's one other example that's such a special example of facilitated diffusion that we give it its own name, and that is the movement of water. Okay? Water exists in the extracellular fluids, very abundant, right? Most abundant item out there, and it's abundant in the intracellular fluids, most abundant. But water is also charged, remember. So it's not going to move easily through this phospholipid bilayer. So we could talk about a sodium ion or some other charged item and say that it needs help in the way of a channel protein or some kind of carrier protein and call it facilitated diffusion. But when we talk about facilitated diffusion of water, and it would need a special protein, right? Because water is charged, it's not going to go sneaking through there. We're going to call it something special because water is so important. Okay, so osmosis would be the facilitated diffusion of water only through the selectively permeable membrane. And again, this would occur from high to low. So wherever there's more water, it'll move to where there's less water. It doesn't have to move the same direction as other dissolved items. Okay, it could move in completely different direction than sodium might or chloride might, but it's always going to move, if it's passive, from a high to a low position. So 2 things to remember for a passive process: it's always high to low, and it's always not going to, there's going to be no energy involved. And then within that category, we can talk about simple diffusion, facilitated diffusion, osmosis. Okay? I think this is a good place to leave it. And we're going to dive into next a little bit more about osmosis, because the water is so important, and keeping track of those fluids is so important for good, healthy cells to function. Okay? Till next time.